Hi, in this video I'm going to show you how to use my Matlab tool for easy setup of the Abaqus damage plasticity model. Let's take a quick look at Abaqus to see what we are doing here. So what this tool should help you is to set up the concrete damage plasticity model. And when you use my tool properly, you're going to produce something that looks like this. You're going to have a density, you're going to have elastic material parameters, and you have all the parameters needed for the concrete damage plasticity. This starts with the plasticity parameters being the default values, but you can also adapt that in my tool. For understanding these parameters, just refer to the Abaqus manual because they are described there very properly. There is also a viscosity parameter which should improve the stability of your calculation. I recommend, depending on your problem, values between 1e minus 3 to 1e minus 5. So the tricky part of that model is actually the compressive behavior and the tensile behavior. You have to tell the software which yield stress you have corresponding to a displacement or to an inelastic strain or to GFI, which is the fracture energy, and you're going to produce just a linear softening curve. But there is also the same thing for the compressive part, with the exception that you can only use inelastic strain values for your horizontal axis, kind of. And yeah, and there can happen a lot of issues if you don't know which yield stress and which data you should use here. And my tool should help you to easily set up these curves here just by typing in your compressive strength and a few other parameters. So the only thing missing here is the damage curves, which is just the same thing in here, just with the exception that you have to define a damage parameter for your corresponding inelastic strain values here. This guy up here is another parameter responsible for the stiffness recovery when you reload from compression to tension. The default value here is 0, and in my tool you cannot change that. So if you have to change that, you can take a look at the input file, how that looks like if you specify another parameter here, and just copy that line in the input file you create with this tool, with my Matlab tool, and then you have the opportunity to define a varying parameter for this thing. Yeah, pretty much the same thing for the concrete tension damage. Here again, the default value here, the compression recovery. So when you reload from tension to compression, you have full stiffness recovery, and my tool is accounting for this effect. So the default value produced by my tool is 1 here. All right, let's take a look at my tool. So just follow the instruction in the description of this video and refer to my GitHub site to download everything you need. You're gonna need the .m file and the .fig file. Make sure you copy these two files in the same folder and run the m file in this in Matlab 2018 B or newer. I'm not quite sure about older versions, but I can guarantee that it works with the versions 2018 B or newer. So once you open the M file, just push the run button up here, and this window should appear. You're gonna see 4 windows. The first one shows you the compressive stress over the inelastic strain with the compressive damage over the inelastic strain. This window down here shows you the tensile stress over the inelastic displacement and also the tensile damage over the inelastic displacement. So for the tensile behavior, this tool provides curves which are type displacement. This makes sure that you have mesh independent results because, as you know, concrete, if it fractures, it's a very localized fracture, like a crack, and you're gonna have specimen length dependent softening curves for your tensile behavior, but also for your compressive behavior, actually. In these 2 windows, you're going to see the plastic strain over just the values that are produced here. So to explain that, I'm gonna just show you quickly the Abaqus manual. So this is a very important thing to understand for this model, that this model has inelastic strains or inelastic displacement, but also plastic displacements or plastic strains which are not identical. The difference is that for the inelastic or cracking strain values, this program or this material model uses the initial stiffness for unloading. So you see that here. And for the plastic strain, it uses the damaged stiffness for computing the plastic strain. So of course you want to make sure that the plastic strain is always increasing and never zero. And in my tool, this window helps you to do that. You will also get a warning here or here if you get a decreasing or negative values for your plastic strain. This was one of the main issues I had when I started to use the Abaqus concrete damage plasticity model, that I didn't fully understand what the difference was between the inelastic strain and the plastic strain. The difference again is that the inelastic strain, which is actually your input data that you type in this field in Abaqus CAE, and the plastic strain is getting computed by this equation here, and this is kind of and there you see it. Abaqus will issue an error message if the calculated plastic strain values are negative and or decreasing. Yeah, this is everything you need to know about that. Okay, let's head to the parameters. In the first field up here, you can specify your material name. When we take a look at Abaqus again, just make sure that your defined section here has already the same name as your material. For a practical application here, you can just create any material here, just a dummy material with only elastic properties, because you're gonna exchange everything that's written in the input file with some lines that I'll tell you later. So just make sure that you have the same name here as you have in your concrete section, in your section definition in Abaqus. All right. So this is the material field, the material name field up here. So down here there are the plasticity and numerical parameters with already all the default values typed in for you. Down here, probably the most important field is the material or mechanical parameters, starting with the compressive strength. And then there is the Young's modulus, tensile strength, and the tensile fracture energy. So here, just always start with the compressive strength, because you're gonna get all the computed material parameters from this value for the rest of the parameters. So for example, if you type in 35, you're gonna get all the pre-computed parameters, which you can now change if you want. So if you feel like reducing the Young's modulus a bit, just do that. But keep in mind, once you change that again, this will change as well. So just always start with the compressive strength here. If you are not quite sure about these parameters, especially for about the tensile fracture energy, for example, the FIP model code provides some information about the fracture energy, and with the help of that, you should be able to understand all these parameters. Down here, this is so the name of the variables is according to the Eurocode 2, the Eurocode 1992 about concrete. So if you want to have a definition of all these parameters of the variables here and the names, just refer to that standard. All right, I'm gonna skip that for a second and head directly to the damage for the compressive behavior. So you are able to define compression damage limit. So this is the highest damage, the maximum damage that will occur in your model, and this is the compressive damage at the the compressive strength strain. So when you reach your compressive strength. This is actually just part of the boundary conditions for the polynomial function here. So this is actually the red curve is a polynomial function, third order, and these two values are part of the equation system, of the linear equation system that will compute you this curve. Just that you know, if you have higher values for compressive strength, your stress strain curve gets more brittle, which means that these two values, so the strain limit and the strain at compressive strength, will get closer and closer. So your behavior is getting less ductile. And since this guy here is located at this strain and this guy is located at this strain, of course this gets very unhandy, you know. So at some compressive strength, this will deactivate, so you can only use that one, and this polynomial function turns into a polynomial function second order. So just with one boundary condition less, so this boundary condition will disappear from the linear equation system. All right. Here you have the possibility to define your data points density. So if you use the maximum of 8, you see that until reaching the compressive strength, you're going to have 8 data points. So later, when I activate the softening branch, so when you get decreasing values for your compressive stress inelastic strain curve, you will also be able to define the values for the softening part. Or you're gonna have the same values on the left as on the right. All right. So for the damage for the tensile behavior, it kind of works the same, with the exception that this curve is an exponential function, and you can only specify your tension damage limit, so the maximum damage you will reach. The same thing with the data points here for just the softening. So this is always per branch actually, since you don't have any hardening. In this plot, you can only use it for the softening part. The hardening, of course, is just linear elastic. The Peta value here is kind of a weighting factor for damage or plasticity. If this is 1, you have no damage at all, so you always have the initial stiffness when you unload. And when you have 0, you have no plasticity, so you're gonna so if you unload, you always go through the 0 point here. And we want to have something in between, and also we want to have a very high beta value, and because in my experience, when you have lower beta values like 80%, you have very high damage values for very small inelastic displacement values, which is a pretty quick damage, and this will probably cause numerical problems, which is the reason why you get a warning message here if you have too small values for beta. I recommend using anything above 90%, or even better 99%, because you're gonna still get good results for this value. Okay, so now we talk about the compression softening. As you know, for the tensile behavior, when you have strain on the horizontal axis, when you have tensile stress over strain, your results are depending on the element size and the specimen length. And the same thing actually happens for the compressive behavior. And I did some nonlinear analysis of big concrete structures, and I saw that actually accounting for compressive softening is very, very important, because you're gonna get just random results for your load history and whatever you want to calculate. So accounting for that is actually quite important. But once you account for softening, you have to think about regularizing your results, right? And this is not available by default. So what you can do when you account for softening in the compressive part of the model is you can always tell the software which characteristic element length you have, because then you'll be able to compute the, the, the fracture energy for the compressive behavior as well. Because with the characteristic element length, you are able to compute the inelastic displacement out of the inelastic strain, and then you can have the area underneath the curve again, and with the help of this ruler here, you can then weight these values here that you have a specific fracture energy for your compressive behavior. So this ruler, what it does is it tells you the tensile to compressive or compressive to tensile fracture energy ratio, which is about 250 to 300. And when you increase that value, you're going to notice that this curve shifts left, which doesn't mean that it's shifting left. It's actually shifting right. So everything right of the compressive strength shifts right so the weighting factor is of course 0 here and 1 here, and there's another scalar factor which moves every value here to the right, this one the most and this one the least, and so there is a loop in this tool that will iterate this weighting factor as long as it meets a certain tolerance for the area underneath this curve. So once again, if you want to account for compressive softening, make sure you have a regular mesh, which means that you should have kind of the same characteristic element length, at least in those parts that have the Abaqus concrete damage plasticity model assigned. And yeah, just type in your characteristic element length here, decide for a ratio, for example 300, and then your model is actually producing regularized results for this characteristic element length. If you at some point change your characteristic element length, you have to change this value as well, because then your results will be the same again. If you don't change that, you will produce different results with a different element length. So this value has always, whenever you change your mesh, you have to open this program again and then change this value again, because all the parameters, all the values, all the inelastic strain values here are getting adapted to produce the same results with a different mesh. This is just how it is, and this is the only possibility to kind of create this workaround that you have, that you can control the mesh dependency for the compressive part of this model. All right, I guess now I'm going to show you how to practically use this tool. I'm just gonna open a new sheet, which you can do up here. Type in yes, and this will open again. Let's say you're happy with all the default values for plasticity and numerical parameters up here. You probably want to have viscosity damping like 1i minus 4, and let's say you have a compressive strength of 56, and so as I said, the Young's modulus is getting computed automatically. If I want to change that, I can do that now. Like let's say I want to have a pretty number here, and the same with the tensile strength. So this is the pre-computed value. Let's say I want to have something different, like 3.8, and the tensile fracture energy is actually quite high. I want to change that as well. Let's make it 0.14. All right, so I'm gonna start without compression softening, just so you see what the situation here is like. You probably noticed that there is an error message here that you have invalid compression data, that negative and or decreasing plastic displacement occurs, and it tells me I should reduce my damage. All right, let's do that. Um, you see that there is a decreasing value of the plastic displacement. So we want to have this kind of hill up there to be a little bit lower. So as I said, this compression damage here is located at the strain at compressive strength. So we might just want to reduce that a bit, or even increase it a bit. And you see how this thing moves. And now you have valid plastic strain data because this is all increasing. So we are happy with that. With the tensile strength, you probably didn't notice that, and I didn't too, that this thing is going to change if I, of course, change the tensile strength. So this thing is going down. So let's be happy with 3. And let's say I want to have 70% damage. Doesn't really matter here because that's not that hard to account for that. Let's just change that for this now. Let's say we want to have 5 values per branch. So this changes as well. We are happy with the beta value, probably just for fun. Type in 98, and you're gonna hardly notice anything. So probably 90%, and you at least see something. All right, I'm gonna increase it again. All right, okay, so this is without softening. And for example, you would use that if you have experimental data for this kind of concrete and all your parameters, and you have parts in your model that don't have a very regular mesh. You don't want to actually account for the softening because you are afraid of the mesh dependency. You're gonna apply that. Material for these parts that are not very regular, and for the regular parts, you can now activate the softening branch. So the softening branch is now this actually that branch here didn't change at all. It was just the softening that was added to this plot. That's why this thing got a little bit smaller here. But this hardening isn't affected at all. Okay, and now you have the softening. And let's say we have a characteristic element length of 50 millimeters. So just let the program compute for a second, and then you can adjust the GFI ratio as probably, I don't know, let's say 250, and you're gonna have this curve for your compressive behavior. Now with lower values for the stress, you can also use higher values for the damage, because the problem is when you have a plateau of stress, you of course cannot you cannot increase your damage value anymore because you're gonna produce decreasing values for plastic strain. But this works with the softening. With decreasing values for compressive stress, you are allowed to use use higher values for your compression damage. So maybe let's just start with 70%. So you notice that this plateau is it was going up a bit, but you still have the error message that you have invalid compression data due to the negative or decreasing plastic displacement. So what we are trying to do now is, since we kind of already decided for 70%, is we gonna play with that ruler a bit. You saw that the curve is going down a bit, so we actually just want to have the other direction. So we're gonna put that up. So okay, now we have this sorted out, and we have the error message for the compressive damage data now. So I'm just gonna try to decrease that a bit. So now we are actually all set. So okay, if we are happy with this data now, we can save that to a kind of certain file. Let's just say we call it CDPA, and just can open it again if we later want to edit it. So you can actually just go to the place where you saved it and can open it here. Let's just try that if you kind of erase everything you just created and you want to restore that. You go into that place where you saved everything and then open it, and you should have all the parameters you used before. Now, since we have no error messages left, the program allows us to export our data. So let's just put it on the desktop and say CDPA param. Okay, so we saved that now, and so we now want to take a look at this file. So this is the file we just created. So let's just review that. We have a material called CDPA. We have the density of 2.4 E minus 9 tons per square millimeter, per millimeter per cubic millimeter. We have the elastic parameters of 38,000 megapascal. And then we have the concrete damage plasticity parameters that we typed in here. We have the concrete compression hardening that you see here with the highest value of 56 here. And everything else is, as I said, type displacement, and yeah. So this is actually what we want to include in our input file. So let's head to Abaqus, and you see that I prepared like a test model for that. We have our parts, we have our assemblies and everything that you need to know. Like once again, the most important thing is we have a material that has the same name as in our that we specified in our tool, and the section has the same name in its definition. We have, so normally your Abaqus probably runs in the temp folder, but you can actually set a working directory there. So I just created for this test a working directory on my desktop. So this is the CDPA test working directory, and everything that you need to calculate this example is gonna be stored in this working directory. So when I have a job created here, I can make a right click and push the right input button there. This is just because I tested it before, and we push OK, so it overrides what I already had in this folder. So when you start right away, the only thing that's there is the input and the CAE file, and so just copy the text file you just created before, this one, into that folder, and now you have to open the input file and just scroll down to where it says materials. And when you go to my GitHub site, there is this README file where you can just copy that line to this input this input file. You can actually delete all of that from boundary conditions all the way up to materials, and then just paste it in. Just make sure that this has the right format. And with this include function here, you're able to define an input file here for your whatever comes here. So you can actually do that for all kind of stuff here. But now you want to have your the name specified for your text file there. So actually that name, we want to copy that here. So now push save, and we can actually close that. And then we go back to Abaqus, where we can now submit that calculation. And now we actually modified the input file, so it has all the data we just created with our damage plasticity tool. And that's actually everything you need to know about that. Just one thing, one like basic thing, background information of that. So of course the data that Abaqus gets from this tool is not the pretty curve here, the blue one, but it is the multilinear approximation of that curve. And of course, the area underneath the curve changes with the density of the dots. And so what I did was I there in the code there is an iteration where this value is getting adjusted, that actually the linear approximation of that curve meets the curve or the area underneath the multilinear approximation is actually having that fracture energy, not the blue one. So the data that you give to Abaqus is having this fracture energy, and the same here. So just that you know that this value for the smooth curve is getting adjusted, that actually the multilinear approximation has this value. All right, I think that's everything you need to know about this. Once again, just always start with the material parameters, with the compressive strength. If you're not sure about all the other values, just stick with the initial ones, because for the lower strength concrete, these values are computed with equations that you would probably use yourself, like the model code equations, but also the ACI equations, especially for the Young's modulus. For the higher strength concrete, I use the ACI equation, like 4,700 multiplied by the square root of FCM and something like that. Yeah, and just always start with low damage, and then you get a feeling on what parameters you want to use, and it's kind of hard to set up this model, but this tool should really help you to make it more easy. Just maybe a few quick words about high strength concrete. So for example, if you have a concrete that has a compressive strength of 100, this model gets pretty sensitive with lower values of ECM. So with higher strength concretes, you have limitations of your Young's modulus that are more narrow than with the lower strength concrete. So if you actually want to have a Young's modulus of 30,000, this is not allowed. So this will get increased by my program. This is not a mistake. This is on purpose, because this curve is getting pretty unrealistic if you have very low Young's modulus, very low values for Young's modulus here. Yeah, and this is also the effect that I told you before, that if you have high strength concrete, this curve will become a polynomial function second order. Of course, that's not part of the polynomial function. That's just a plateau. And with the high strength concretes, the amount of damage that is allowed is decreasing and decreasing. So probably with such a high strength concrete, you're not going to be able to have more compressive damage limit than 30%, 13% with, for example, that. And you would get error messages if you would choose any compressive damage that's higher than what's allowed in this tool. All right, I hope this helps you with your work. As I told you, I in the context of my master thesis, I am dealing a lot with concrete simulations, nonlinear concrete simulations, and I actually used the user material, and I wanted to use the Abaqus concrete demonstrability model just for comparison. And to set up this model, it took me a very long time and a lot of tears. But I'm very happy that I could look through it and understand everything. And yeah, I'm very happy to share with you all the things I've learned. And please keep using my tool, and I hope it helps you with your work. Well, thank you.